Dear learner, in continuation with the chapter current electricity, today we'll discuss about potentiometer. We'll understand the working of potentiometer. And after learning to this topic, you will be able to explain the working of a potentiometer. You will be able to compare EMF of primary cell using this device. You will be able to compare find the internal resistance of a cell using this device. Dear students, I hope you are aware with these facts, that is facts of Ohm's law, then concept of potential drop and potential fall, and you are well aware of Kirchhoff's law. Kirchhoff's law means that is summation of I is equal to 0 at a junction, and summation of potential changes in a closed loop is equal to 0. So to start with the potentiometer actually it works on two very important facts. Number one, I must say this is the potential gradient. First one is potential gradient. Potential gradient. It works on this fact. This fact is very important, and for this potentiometer. And dear students, you know why should we learn this about this device? What is the use of this device in our daily life? You know, it is used very frequently, almost in all devices. Right? Sometimes it is used as a potential divider. Sometimes we use it as audio control. Sometimes we can use it as a sensor device. It can be used to compare what I told in the learning outcome, that is a comparison of EMF of primary cell, measurement of EMF of a cell in the with the help of standard cell, and we can find the internal resistance of the cell. So it has got much importance in the world of electricity. Now see, potential gradient. What potential gradient is? It is exactly the a potential drop, sorry, a potential drop per unit length. Let us understand the concept of this potential gradient with this simple circuit, and let us try to answer these three simple questions. Then we'll be able to understand potential gradient. See, let me consider a wire AB. AB is a resistance wire having resistance. Let resistance of the resistance wire, that is AB, is equal to 10 ohm. Okay, and we allow some current through this wire with the help of this cell and the rheostat RH. Okay, let us allow 100 milliampere current. 100 milliampere, this is simply equal to 0.1 ampere current. Length of the wire is 100 centimeters. Okay, this is given. Now, let us answer these three questions. Nothing more to do. Let us answer these three questions only. What is the potential difference VA minus VB? That is, what is the potential difference VA minus VB? Let potential at A is equal to VA. Then, what is drop of potential? Resistance of the wire AB into current in the wire AB, that is equal to what VB. So if you want to write VA minus VB, then this is equal to RAB into I. And as per our consideration, this is equal to 10 ohm multiplied by 0.1 ampere. That comes to 1 volt. Okay. What is the second question? Let us see. The second question is, if the potential at A is 4 volt, that is potential at A is 4 volt, it is 4 volt, VA is equal to 4 volt. What is the potential at B? Very simple, from this relation only we can write VB will be equal to, let us follow this one. VA means 4 volt minus, this is 1 volt, equal to almost 3 volt. Okay. Next question. Calculate the potential drop per centimeter in the wire. Okay, then what is the total potential drop across AB? VAB is equal to 1 volt. What is the length of AB? LAB is equal to 100 centimeters. Then The potential drop per centimeter. Let me write this as K. K is equal to potential drop per centimeter VAB by IAB. That is LAB. LAB. That is equal to 1 volt by 100 centimeter. That is a 0.01 volt per centimeter. Alright. This is the potential difference, potential drop per centimeter. Now, let me ask you, what are the factors on which potential drop per centimeter depend? This is obviously the potential gradient. This is potential gradient. Does it remain constant along this wire? That is, in any section, if we consider the potential gradient or potential drop per centimeter, that is, if we consider 1 centimeter here only, 1 centimeter here, then potential drop between P and Q has to be how much? 0.01 volt. If we consider here potential drop per centimeter equal to 0.01 volt. Is it true for the whole wire? Is it same? Let us try to understand with a suitable expression. That is a K equal to, but it till K is equal to VAB by L. Okay. VAB by L. What is VAB? VAB is simply equal to R into I by L. What is R? R we can write rho L by A. R into I by L. L cancel. So this comes to rho by A into I. Therefore, what we see that K is equal to rho into A into I. Is it? This is the potential gradient. Now, the factor which can affect the potential gradient, this is cross-sectional area and the current. Resistivity, as the material we have used the uniform wire, it is made up of the whole wire is made up of the same substance, so resistivity remains fact. Still, the potential gradient will depend on I and A. If area of cross section everywhere, if we take a uniform wire, everywhere the area of cross section is same, then what we can say for a given current, for a given current K, that is potential gradient, is constant, provided the wire is uniform enough. Okay, this is what potential gradient. The first factor which leads the potentiometer, that is potential gradient. Okay, so potential gradient along a uniform wire remains constant, or potential drop per unit length across any section of the wire remains constant, provided the cross section is uniform throughout. Okay, second, again, let me connect this with a cell. Okay, and let me write here, take here a point C, and here the point is D. Okay, now what is the potential at D? Okay, we will consider this. First, what was our consideration? I was equal to 0.1 ampere. Here R was how much? R equal to 10 ohm, and R equal to 10 ohm, and L is equal to 100 centimeter. Now let me know what is the potential gradient. We found it. The potential gradient K is equal to, it was 0.01 volt, 0.01 volt, 0.01 volt. Now if AC is equal to AC is equal to 40 centimeter. Can you tell me what is the potential? What is the potential potential at C? Can you tell me? Potential drop per unit length is 0 point per centimeter, volt per centimeter. Of course, volt per centimeter, 0.01 volt per centimeter. So AC, the length is 40 centimeter. Therefore, 40 centimeter, the potential drop, that is VAC, is equal to how much? This is equal to 0.1, 0.01, 0.01 into 40, that is equal to 0.4 volt. Therefore, potential at C, let us find first. Potential at C, that is VC, equal to what I can write here. We consider VA is equal to 4 volt. So VC will be equal to what? 4 minus 0.4, that is equal to 3.6 volt. Okay, potential at C. Now if we take this, the cell has the EMF zero point 0.4 volt. What is the potential at D? That is the question. Is the question. What is the potential at D? If this 0.4 volt, what is the potential at D? Okay, I hope you can answer easily. With the potential at D, VD, we can write how VA, we're starting from VA minus what is the drop here? What is the drop here? This is the drop of potential 0 0.4 volt. This is the fall in potential, that is 0 0.4, means 4 volt minus 0 0.4, 3.6 volt. Okay, means what we can say. The next question, let us come. What is the next question which arranged here? See, what is the potential difference between C and D? We got two points, one here C, and another point with the cell, then here the point is D. What is the potential difference between C and D? We can see VC is equal to 3.6 volt, as well as VD is equal to 3.6 volt. It means say VCD is equal to 0. If we connect these 2 points, now if we connect these 2 points with any kind of what gadget, can you expect any current through this? Suppose this is a galvanometer. Can you expect any current? No, not at all. What is the reason? The reason is potential difference between C and D is 0. Therefore, no current can be expected here. Right? No current will flow from D to C or C to D. Yes, current will flow if potential difference arises. How we can create the potential difference? Simply, you see, if we make a little this C point, we consider here little little right, then what happens? Potential drop will be more. Suppose this is 50 centimeters. If it is 50 centimeter, then here the potential will be, that is VC, that time will be equal to 3.5. You try to calculate this. How it is 3.5 volt? Now it is 3.5 volt. Here it is 3.6 volt. Means there is potential difference arises between D and C, and current will flow from D to C. But if no current flows through this, then, and it is the result of there is no potential difference. So if no current, just converse, we can think like, if no current flows through the galvanometer connected across C and D, then we confirm that C and D are at same potential. C and D are at same potential. Yes. So C and D will be at the same potential, no current flows through this. Therefore, if we a sliding key, and we can balance for this the galvanometer for the zero deflection. Sorry, there is a battery and then a galvanometer for zero deflection. What happens? We can see the potential at C and potential at D same. and this is only possible if the potential drop across this wire, that is VAC, VAC is equal to E. And VAC, that happens when, then what we can say, that EMF of the cell is very much equal to VAC. Why EMF? Why EMF? Why not the terminal potential? Because no current is flowing through the cell. The cell is here open circuited. So first we have here we have achieved no current condition, that is open circuited condition of the wire, and we are going to equate the EMF, not the primary potential, but the EMF is equal to VC, and in turn what we can write is equal to K into L of AC. This is the These are the two facts which we can use in a potentiometer. Okay, now let us know what is the first point. For the first point we got the potential gradient. Potential gradient remains constant, and if a balance condition is achieved with the help of a galvanometer, then E is equal to VAC, that is E equal to K into L, or what we can say, E is proportional to L. Okay. Now let us know how this potentiometer can be used to compare EMF of two cells. How to compare EMF of two cells? We can. One more thing, you see, regarding the sensitivity. Before comparing EMF, we should discuss this. What are the potential gradient we got? Potential gradient here we got 0.01 volt per centimeter. No, this potential gradient can be reduced further and further easily. That is potential drop per centimeter. Per centimeter potential drop here to 0.01. You see, we were taking 100 centimeter long wire. If we take 1000 centimeter long wire, the potential gradient reduced to 0.001. Now, 1 centimeter long wire will give a potential difference of 0.01001 voltage, and the potentiometer becomes more and more sensitive. Okay, now let us come to the fact, that is uh, comparing EMF, comparing comparing EMF of two primary cells. Very interesting experiment. Okay, let me pick one potentiometer from the website. Thank God, and thank to this organization, they have prepared. This is from Amrita Vishwa Vidya Pitham. Okay, SIDAC, and they are preparing. They are giving O-lab facilities also, and this is one of the diagram I want to share with you also. You see, this is the potentiometer, and let me keep it here. Okay, this is the, now let me show you what a real potentiometer is. Yes, you see, this is the potentiometer. This is wire itself represent the potentiometer. This is a wire having 10 turns here, and each turn is 100 centimeter, like this, 10 turns, and the total length of the wire becomes 1000 centimeter, like this. They are connected like this, and so on. 10 turns are there, and it the total length becomes 100 centimeter, and more the longer the wire, more will be the sensitivity of the potentiometer. Now how to connect it? We have to first we have to think to supply some current to this wire. Current, the source of current, this is the source of current. Let us make this terminal positive, to connect this positive, and now a switch, then this to this, and this terminal will be connected to the sliding key of the rheostat, and then this terminal will be connected to here. You see, now current will flow. If we make the switch on, then current will flow, and from the ammeter we can measure the current, and with the help of rheostat we can control the current. Let us fix the current as 100 milliampere. The current is 100 milliampere. Okay, now you see what is happening. This is called primary circuit. This circuit just to allow current in the potentiometer. This is primary, in the primary circuit. Okay, now see, if you want to compare EMF of two primary cells, what you need to do, see, what you need to do here. Um, you have to connect a cell, let its EMF is E1, and here another cell, the EMF is suppose E2, with the help of a two-way key. Let me use a two-way key like this. And this is again in go. Let us use this key and a galvanometer. And to protect the galvanometer, we'll use a high resistance box. Okay, and then to the jockey, we'll find the balance point here. Suppose E1 is connected to the galvanometer. Now this time what happens, then if you find the balance point here, suppose at L1 you find the balance point, then what you can write that E1 is equal to K into L1. Okay, very simple theory. E1 will be K equal to L1, because this is only possible balance condition or zero deflection. Here zero deflection is only possible when the potential drop from this point A to J and potential drop across E1 is same. That is E1 equal to K into L1. Now, to proceed, what we have to do? We will disconnect this. We have to disconnect the battery E1, and we will connect E2. Okay, we will disconnect this one, and now I want to connect E2. And we'll get some balance point, get a balance point somewhere else, and let this is at L2. Okay, length means what? Length means we are measuring the total length of the wire starting from A, 100, 200, 300, 400, like this. So we will get for E2, we'll get E2 equal to K into L2. Now see, since current is kept constant, so K will remain same for both the cases. If K remains same, now we can say E1 by E2 is equal to K cancelled out, so L1 by L2. So finding this ratio only, finding only the balance point, you can compare the EMF of two primary cells, and exactly you are comparing the EMF here, because we are not allowing any current through the cell, hence it is open circuited, and we are talking about only EMF. Now, if one of the is cell is standard, if E2 is standard cell having known EMF, having known EMF. Okay, and that is very easy to find a standard cell. It's very easy. So known EMF. Then what we can find? We can find E1 is equal to L1 by L2 into E2. We can find the EMF of the primary cell also, and we can easily compare the EMF of two given primary cell. Okay, one more thing we can do. If K is known to us numerically, if the value of K is known to us, that is knowing the current and resistance, just we have to know the current and resistance, we will get the potential drop across the total wire, and then we can find the value of k by 1000 we can do, and we can find the value of k. Once we know the value of k, we can find EMF from the single observation, that E1 will be equal to k into L, k into L1. So with this simple experiment, we can do both the things. We can compare the EMF of two cells. We can and find the EMF of a primary cell. Dear students, it is a very interesting and important at the same time. And please go through this once again in this video, and try to understand what working of potentiometer. Hope it is clear to everybody. Thank you very much. Thank you.